given this P. It's not necessary. I mean, you can be quite honest. You can say, I don't know the answer, or this is it, as far as I can tell. If you have a better answer, tell me. I think it's important to be that way. Anyway, you can look at that. If you Google, you'll find this person's interview. His name is Louis, Louis, Louis Nurnberg, Nirnberg. And Nurnberg is a there's a long Wikipedia page on him. He's a pretty major figure. It's also on my Facebook page. So if you go there, you'll be able to. I think it's a public post. See. So I was we're going to talk about battles, and I wanted to bring up a few points before I got going. One is the fact that now what happened? I thought I did a share. Oh, here we are, share. Okay, I hadn't shared. So one of the things was that we did all these things. I'm not very interested in all the formalism right now. But I'm more interested in telling you the behind the scenes picture of how this thing works. All of this is formalism that Linda had put in, and it's in the papers. It doesn't shed any great light on or insight on what we are doing. But what sheds insight is this picture. So remember, I was telling you guys about these stochastic battles, this non-strategic two-party battles, Markov battles. And the way the battles go is as follows. You have a battlefield, which is a lattice. For example, this is a lattice, right? This is your battlefield. And in every iteration, you randomly throw some negative numbers between, let's say, -1 and -2, and then randomly throw some positive numbers, which are like +1 and +2. You can make it -1, -2, -3, +1, +2, +3, or just -1 and +1, for example. You don't throw a 0. And of course, they don't have to go to every lattice side. And eventually, as in every iteration, you keep throwing some, all the lattice sides will typically get filled up because it is not a very extended space. Actually, if it's an extended space, that leads to another problem. So let me not get into that because we didn't really explore it now that I think of it. So the idea is that, this -1 and -2s or whatever numbers you select, these are your, what I called force levels. So these can be your ammunition level. It can be a simple rifle. It can be, an automatic rifle. It can be a hand grenade, whatever. More lethal it is, the higher the number. And the reason why it's minus and plus is because simple algebra dictates that if in a close spacing, small area, two opposing soldiers end up, they'll hurt each other. So the value there will go down or go up depending upon who's doing what. And if both are very badly injured, it will be 0 because they have now become ineffective as fighters. So that was the point of the battlefield. So you keep throwing in every iteration. Anybody can do that, really, right? I mean, you can draw up your own code in your favorite language. You don't need a big machine, and you can run this problem. And epsilon A and epsilon B are essentially the percentage of the lattice being occupied by side A and side B. Okay, so 0.6 means 60% of the lattice is occupied by side A, and that is being maintained in every iteration, because in every iteration, if the lattice has 2,500 sites, only 60% of 2,500 can be thrown on the lattice. Now you can see something already, that if a lot of soldiers are thrown on the lattice in every iteration, and you have a finite number of soldiers in your bank, you are eventually going to run out of soldiers to fight with, and you might lose, right? So then the reserves therefore matter, and how much of the lattice you throw whom with what weaponry matters. In this particular problem that I'm showing, you can see that the force levels here, this is S plus and S minus, if you will, of side one versus the other side is only one. And it turns out that if you observe, there are more A's than B's, and the number of reserves on both sides is large. But it's a dumb battle. It's a stochastic battle, right? There is no intelligence in the battle. So if there is more A than B, it's trivial to conclude that A would win because A would slowly kill off the Bs. And that's exactly what happens because the plot on the right is the probability of finding species B. And as you can see, as time progresses, the probability of finding species B is going down because the number of soldiers from B are no longer there. They're dead or ineffective. So this is like that's why I said non-strategic trivial case example. And this is something very similar, excepting here it's more subtle. For example, half the lattice is being occupied by A and B. So in terms of numbers, they are even. In terms of force levels, both sides have 1, 2, and 3. Plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. However, the weights associated with, let's say, the negative side, which is the attacker usually, and the positive side are not the same. So negative side is not throwing ones and twos, it's only throwing threes. Okay, that's what this means. The positive side is throwing ones and twos with low probability, but threes with higher probability. So they're very close, but they're not exactly the same. But as you wait long enough, you begin to see that the probability of finding species B, which is using all the force levels, is ever so slightly creeping upward. So the solid line here is simulation, and the data points are from theory. That's how she has done it here. So this is a very expected result because there is more diversity, although everything is the same, but even the diversity here is helping out side B, and side B is essentially beginning to dominate side A, which is the attacker group here, the negative group. All right, so let's now move to more realistic battles. So I have to explain to you what this realistic battle is. Let's first observe that the force levels, again, are 1, 2, and 3. The simplest battles would be +1 and -1. And these would be typically the ancient battles which were fought with limited weaponry. In fact, some of the battles that we studied with the simplest possible force levels reminded me of the battles I had read chronicles of that were fought by Alexander the Great. So relatively simple weaponry, numbers, the kind of strategy in terms of how many soldiers they put on the field. These were things that Alexander the Great excelled at. But in terms of force levels, of course, in those days, not that much was available. A more advanced battle already is 1, 2, and -1, -2. In fact, much of the Iraq war we modeled with 1 and 2 only. Then there can be asymmetric battles. For example, you can have one side may have fewer forces, but may have vastly more powerful soldier resources in terms of what they can fight with. So this also is a very important case, but asymmetric case, we really haven't studied very much the asymmetric case. Now, this is an interesting point that I want to introduce. I'll come back to it very soon. Suppose you are the attacking army and the defenders are already there because you are attacking the defenders' territory. Defenders are there already. This was the case in Iraq. US forces were basically deployed in Iraq to capture Saddam Hussein and remove him and do whatever is needed. But the Iraqis were very good soldiers and they had excellent weaponry and basically high levels of expertise. And they knew the terrain and the land very well. The Americans did not know that. And so the Americans were very strategy dependent. For example, if you have an area where you know there are enemy soldiers, what do? There are two things you can do. You can move ahead in that direction and directly engage the enemy soldiers. And two, it may be wiser to move away from the enemy soldiers such that your pack size of the part of the army that is involved is larger, which means less soldiers from enemy side will likely be able to break you. You see, both are viable strategies if you think about it. Our gut feeling is be aggressive, kill them off. But there is nothing wrong in being conservative and actually backing up. So we decided to try it. Okay, so this is what I'm going to discuss. You see, at the end of the day, this is a statistical physics problem, but it is framed as a battle problem. And I'm not going to tell you about that part of the study, but we studied also the terrorism problem. I mentioned that about the Taj Hotel attack and so on. And there are many areas that we never studied because, we spent a long time on it and it was not easy to publish the papers in those days in this kind of study. We were too far ahead of the time when this would count as serious science, but it was. So this is from a talk I gave a long time back, but here is the outline of the problem. What is a win? You have to ask this question, right? What is a win? I mean, it's like Trump saying we won. Won what? What did you get? In fact, by every measure, he has got nothing. Strait of Hormuz was open, now it's closed. Many Americans have died. We have our bases in the Middle East have been pretty badly destroyed. It's embarrassing. So what exactly did he win? I mean, nobody knows, right? As usual. So you have to define the winner somehow. And second, it's also a matter of strategy. So about this win or loss in 2004, when all of this was going on, look at the level of confusion among the leaders. So here it comes. So George Bush was interviewed in 2003 when the battle was at pretty much in its early phase and Saddam was captured. So Abraham Lincoln, he was obviously in a naval vessel. President Bush on Thursday praised the toppling of Saddam Hussein as, quote, a job well done, unquote. But he warned that the battle in Iraq was but, quote, one victory in a war on terror, unquote. See the confusion. Thus far, nobody has been able to establish, and at the time, they had no data that Saddam Hussein was involved in any terrorism. He was a very bad guy in many ways. He was very bad to his people. He was a murderer. He was a dictator. But people in Iraq by and large, were not complaining. It was an American problem because America wanted oil. In fact, it so happened that in late 70s to early 80s, so about 20 years before that, when Saddam Hussein was relatively new in power, my aunt, my mother's eldest sister, she and her husband, they were posted in Iraq for about 3, 4 years because Iraq was building some of the major dams on the Tigris and the Euphrates rivers. And my uncle, who was a very accomplished civil engineer who had built some of the major dams in India, such as the Farakka Barrage, you may have heard the name, Vivek. My uncle was responsible for much of that work, as well as many other big dams. So he was there. And so I have heard from them that Iraqi people were not actually unhappy with Hussein at the time. They were pretty okay with him. Of course, they would have rather not had a dictator, but in most parts of the world, kings or queens is very common. That has been the federalist model. And dictators are equivalent of each of them because the powers are similar. A dictator now has become a bad name, whereas King Charles is perfectly fine, except King Charles has no power, right? But that is not the case for most other kings. I mean, King of Spain has more power, and so on. Anyway, so confusion about Saddam Hussein and who is the terrorism. First confusion. Second comes another Bush one. If we were to leave before the job is done, what job? In my judgment, the Al Qaeda would find a safe haven from which to attack. Bush says this 3 years later in 2006. Bloody Al Qaeda was not in Iraq at the time. Al Qaeda was sitting in Afghanistan and Pakistan. Okay, so this is another. Everybody knew it, excepting these people. God knows how. Defense Secretary designate. This was a smart guy. I've actually met him once. He came to Buffalo. Defense Secretary designate Robert Gates yesterday said, US is not winning in Iraq. One final piece of truth from somebody who was actually a military man and a politician. US is not winning the war in Iraq. December 6, 2006. Okay, this was just before Bush's statement of 2006, right? October 18, December 6, literally a little over a month. And finally, December 20th, within 2 weeks of Gates' statement, who is this? Bush again says, US is not winning the war in Iraq, Bush says for the first time. So obviously Gates told him, what are you doing? I mean, you're talking nonsense. Go say the right thing. And Bush did that. That was good about Bush. Trump would never have done that. Now comes this thing. Now here is somebody who is eminently believable because Colin Powell was, a 5-star general and really amazing person. Also somebody I've met because he was invited once to Buffalo. So I agree with the assessment of Mr. Baker. Baker was the Secretary of State. And Mr. Hamilton, I forget who Hamilton is. I think I mentioned it somewhere. Oh, Lee Hamilton. He was a congressman. Not a good guy. He's dead now. Powell said, referring to the study group's leaders, former Secretary of State James A. Baker III and former Indiana Congressman Lee Hamilton. James Baker was a very good tactician. He was a Secretary of State under George H.W. Bush, Father Bush. The situation in Iraq is grave and deteriorating. See, military people tell you the truth, and we are not winning, we are losing, it says. But we haven't lost. Again, I'm sitting here in front of the television and wondering what is winning and losing? What is the definition? But anyway, then there was the statement made by this journalist. Al Qaeda has now metastasized into new semi-autonomous groups in many nations. Aha, welcome to the reality, because this is something that most people in Asia, in Southeast Asia, South Asia at the time knew. I mean, I remember a conversation with my father-in-law at the time. He was a very, big figure in his field and a very smart and influential man who had retired by then, well retired. He said, what is America doing? I mean, they want Osama bin Laden, yet bin Laden is sitting in Pakistan, as far as we know in India. But why are they fighting in Iraq? And what's the story in Afghanistan? It's like a scatterbrain scheme to do something in Afghanistan without knowing its history. Nobody has ever won in Afghanistan, ever in the history of the world. And you know why? Just the terrain is such that you can't win. Uh, so unless you're a local, and locals won't fight in that terrain because they know better. So we made a very sort of difficult thing, a decision in that thing to go there, but for reasons that are completely not clear. Anyway, moving on. So how do we define a winner? Okay, I had to define a. I mean, I was doing a physics problem, so I had to define a win. I couldn't get away with bluster. So winning, it can be a well-defined mission accomplished. One mission or two missions. It can't be five missions. Well-defined mission. B, spatial dominance, occupation, annexation. Now, modern battles don't go for spatial dominance, occupation, and annexation. Modern battles are not about territorial expansion, usually. But C is what, after many, many gyrations, I came up with as what is winning. Overrun the enemy because the enemy runs out of combat resources. That means money, that means weapons, that means soldiers, etc., etc., etc. So if it is C, then C is more important in mission than A and B. Because A is just a well-defined mission accomplished. You may not be satisfied with it. You may initially think that this mission is the mission. Once I'm done with this mission, I'm done. But then that presupposes that you know exactly what you need to do, which is seldom the case in a real battle, right? You have some fuzzy idea of what you need to do, maybe a little bit less than a fuzzy idea, better idea, but hard to make a very well-defined mission. Spatial dominance was Alexander's goal. Spatial dominance was how King Ashoka's empire eventually reached central Afghanistan from as an Indian empire. It went from Afghanistan on this side to well into Burma and all that on the other side, if I recall correctly. Because he won so many battles. Same, even in more recent times, if you look at the Maratha rulers like Shivaji and so on, they had very, very big empires because they won so many battles. But those battles are gone. We now do more strategic battles. And C, overrunning the enemy and basically disarming the enemy is more reminiscent of modern battles. So what we can now do is we can wage war on a grid. We can take a 2D square lattice. We can allocate forces, attackers and defenders. We can deploy them according to a random number generator of our choice. We can call the attackers blue, for example. That's what the US Army told me to do. Defenders are red. Yeah, I was not doing that. And so one of the program managers who was a mathematician and who was also ex-army, he said, US Army likes to be blue. I said, okay, fine. Henceforth, everything is going to be blue whenever I'm modeling the US Army. So I made it minus and blue.
Blue is good guys, red is bad guys.
Yeah, exactly. It is very funny. So here we are. So we had 500,000 resources. Actually, that's about right. US Land Army now has about 450,000 soldiers, highly trained soldiers, but it's about 450,000 in number. So my guess was completely out of my pocket and was not a bad guess at the time because the numbers were pretty compatible even then. Simple battle, as I said, force levels are 0 and 1, basically 1. Moderate would be 1 and 2, and advanced would be 1, 2, and 3. And just as I told you, battle initiation would be red or defender. deploys at random values with mix of strength values at defense occupation density epsilon r. Epsilon r is the percent of occupied site of the lattice. Defender is in home territory by definition. Defender is also a non-strategic army because the presumption is they're being attacked. So they really don't have much time to strategize, but they are very, very capable, they're very lethal, and they know the land very well. So that boils down to they can go anywhere at any time, right? I mean, imagine a foreign force attacking a country. The home country will be very um, able, very capable and able to defend themselves because the army doesn't sit in one place. The army is always dispersed. Same with the Air Force, same with the Navy. It's dispersed all across, right? By the way, this is also the reason why territorial expansion is no longer a very good strategy because that means your army will have to be more spread out, which means you're able to defend even less. For example, US has outposts in Guam to be able to combat Pacific threats mostly from China, from um, uh, any other country from that side. But it is not easy to maintain these posts because um, they're expensive. They're just communication takes time and all that. Anyway, so and the blue, which is the attacker side, almost always deploys strategically, deploys in such a way that it doesn't overexpose itself to the enemy side, and at the same time, it uh, it uh, it in every time iteration, the army behaves strategically, meaning aggressive or defensive or whatever. And again, if it's a stochastic battle without strategy, as you would expect, it's a 50-50 chance of winning, other than noisy stuff, which is what we showed here. And this is the same thing, but this is how the battlefield looks like. Where red is red and blue is blue, right? So in other words, in this case, um, B is going down, which means that most likely blue is going down, and red is winning. And in part, red is winning is because of the because epsilon r is 53%, whereas epsilon b is 50%. So that slight advantage in numbers is helping because it's a non-strategic battle. Now the question becomes, what does strategy give us? The strategy makes a big difference. Yeah, Tony.
Were you able to invoke any type of like movement penalties? So like the defenders would be able to move more spaces than the attacker because they know the terrain?
Very good question. We were able to do the following. We actually didn't have movement on the lattice, but we had effective movement on the lattice. I'll tell you why. First, before I get to movement, let me point out that the defenders, they could go anywhere. So at every time step, defenders were all over the map. By the way, in this strategic battle, we just deployed all defenders pretty much together. We didn't deploy fresh defenders. So defenders had an initial advantage. And that initial advantage, if the battle was getting longer and longer, then the initial advantage was waning off because the attackers were reinforcing at every time step. That was certainly one strategy that we had used in the studies. I don't remember if the other strategy of deploying defenders periodically was used. I believe it was used, but there were like 6 or 7 students who worked on it, and many of them took off on their own because they got so interested in the problem that I had trouble keeping track of all of their activities. Which is one reason why about 50% of the work we have done has still not been written up, and I don't believe will ever be written up because these people are long gone, and I don't even have some of the core data from their studies in any systematic fashion other than the plots. But yes, the basic point was that defenders were very widely spread out, so they could defend the territory well. In terms of movement, the answer is as follows. that in every iteration, attackers deployed new forces. So a site that may have been, let's say, that may have had a strength of minus 13, in the next iteration may become plus 11 or something like that, let's say, or maybe minus 11. Um, then you can see that somebody went there and there was some kind of battle that happened in that area. So we didn't have any physical movement. Remember, it's a lattice gas at the end of the day. Okay, it's basically a lattice gas problem or a cellular automata problem, or the agents are not really moving, it's the force levels that are moving. Agent movement is a little bit more complicated, so we decided to avoid that. All right, so blue again is the attacker in this case, and there are two strategies, as I said. One is to go towards the enemy, which is the aggressive strategy, which is here, and the other is to go away from the enemy, which is the defensive strategy. So, one is this is the aggressive part, and this is the defensive strategy. This turned out to be an extremely important variable. This range R. Okay, so the range R went like this. The picture that I had in mind is as follows. Suppose you are a soldier who have been deployed, and you want to make sure that you don't lose time, and you make sure that you have made the situation worse for the enemy, because that should be your goal, right? That should be the mission. What do? What would I do? I'd pick up my electronic device and I look at satellite data and find out where my enemy soldiers possibly are. Because things can be seen from space. I'm getting data beamed down from space through satellites. So my cell phone, if it's correctly set up, is going to give me information about where the enemy is likely to be. Okay. So this is R. R is small r. R is how far out I know and how well I know, both of them together. The presumption here is that if R is large, then I don't know very well. My satellite's resolution is not the best. That was what I assumed. And if R is small, that means the satellite is powerful enough to tell me who are the enemies, how close to me. And then I can go or not go in that direction. So a smaller R means higher resolution, higher intelligence in effect, higher resolution of the satellite, higher intelligence in effect. A larger R means lesser resolution from the satellite and less intelligence for me. Yes, Tony.
Previous two pictures that you just showed, those were for non-strategic battles, right?
Yes.
Okay, and then now we're invoking strategy. So would R has no point in a strategic battle because access to information would imply you have a strategy, right?
R is only for strategic battle.
Okay.
R is not there for non-strategic battle, right? Non-strategic battle has no strategy. Yeah. So R is being introduced now, and the way we interpreted R was smaller R means higher intelligence, because I know with higher level of precision who is sitting where. In fact, just to give you a sense of how well this kind of data analysis is, when Osama bin Laden was killed, there was a particular reason for much of the US Army, if not entire all of US Army, to feel very relieved. Bin Laden was hell-bent on destroying America, number one. Number two, Bin Laden was creating trouble for a long time. The first major terrorist attacks that were led by Bin Laden was from 1993 during Clinton time. And at that time, 93, 33 years ago, there was a situation where US had precise intelligence in real time as to where bin Laden was standing from space. Just imagine, bin Laden was very tall. He was 6'5" or 6'6". So during a certain time of the day, if it was not near noon, And because these regions are not very cloudy, bin Laden's shadow often gave away where he was. And I've seen the satellite picture that US had because it was shown on TV. Okay. So I was very well aware from just watching simple news as to how much resolution sitting in space, going just orbiting the planet or in geotechnical what is it, geostationary orbits, they were able to figure out that bin Laden was in this place. However, they missed that opportunity in 1993. And this issue had been brought up in American media at the time several times. That's why I knew about it. So they were hell-bent on getting the guy this time, and they were having a much harder time because bin Laden didn't count on American resolution in 1993 very carefully. He used to be very careful. So then he started living in the caves in the mountains and eventually started to live in Abbottabad in Pakistan. He had obviously protection from Pakistan army because otherwise, you know, he would not be there. But anyway, the long and short of the story is that America's space-based detail on who is where and what is what is astonishingly good. It really is, and it's been good for God knows how long, because what I told you was already 33 years ago. So this is how the battle, you can imagine a toy battle is starting, where you have, this 5x5 grid, 60% is red, 80% is blue, and intelligence is 40%, which means that you have some idea of where the enemies are in 40% range. Okay, so 40% of 5 here. It's 2, basically 2. So you have intelligence over, in this very simple case, over 2 cell length scale. And the best you can get is 1 cell length scale, right? So best is 20% in this super small battlefield, but you have like 40%, which is not too bad, but it's not very good. And the reserve size is only 5,000. Sophistication is 1 and 2. I'll show you this picture, but this picture is confusing. But basically, let me tell you the way this thing works. So you take any point. Suppose you take a point here, this point here, this at this point in the middle. You are going 2 lattice sites to the left, to the right, and 2 lattice sites above, and therefore this entire 3x3 grid, subgrid. And you are essentially figuring out what is the total positive is the other side. What is the total positive number there? So total positive number there should be 2 plus 1, 3, 4, 5, 6. Total negative, -2, -3, -4. So there are more enemies on this side. So R equal to 40 essentially gets you some information like that, roughly. It's a little rough, but it's always like that because it's a grid and it's a percentage. You can't have half a grid, right? So therefore, the question is, where will you deploy? Do you deploy here? Do you deploy there? Now, I had advised my initial students to deploy in the middle somewhere at a 45-degree angle, or if everybody was to the right, go right. Everybody's to the top, go top, or go. If you don't know, then go kind of at a 45-degree angle. Linda, on the other hand, when she did her rule settings, she employed a slightly different technology for it, which I learned much later. But the answers don't differ much because what matters is the range itself. And each of these calculations are run over many hundreds of independent sets. So what you get is an average. So, but Linda did it differently, and this was Linda's strategy, where Linda, for example, took this yellow region, and the way she nomenclatured it completely blew my mind because that's not how I understand things. She made this point 0, 0. She made the downward direction to be the x-axis and the horizontal direction to be the y-axis for reasons that I'll never understand, but that's what she did. Uh, I think she must have started originally here and then she had to switch something at some point. I don't remember. Doesn't matter. But it took me a while to understand this figure now that I was looking at it after many years. Um, the last talk I gave in this problem was probably around 2015-16 timeframe. Anyway, so here, basically what happens is that K35 is the site 35. How is 35 being calculated? This is 5, 1, 2, 3, 4, 5. See that? 1, 2, 3, 4, 5. This is the Y. It should be X in my opinion, but this is Linda's Y. Okay. And K3 is downward 3, 1, 2, 3. So this plus 1 in this study underwent a deployment of -2 and became a -1. See that? That's how it worked. This plus 1 here at K5, 3 became, see, 1 minus 2 equal to -1. This is the -1. So this is how she did her deployment. It's fine. You can use whatever you want, but as long as your thing is consistent, it's fine. It works out okay. Anyway, so at the end of the day, this is what happened. So in this case, look at the final state. The number of blues at the end of God knows how many steps it ran. She didn't say here. A lot of steps, obviously. You see, red has been decimated. Red has become 0. Blue still has 599 soldiers left. Battle is done. Clearly, blue is winning because by our rule, winning meant the decimation of the other side. Nobody can fight anymore. Well, if you don't have anybody, how will you fight? So this was one way to realize that. But look at how chaotic the numbers are. Because this is a real land battle. It's like a Mahabharata war. It's like a true land battle. And if you look at this, this looks like one of those blankets that the grandmother would make for the baby. Whatever color you could find, you stitched it together, and that became your colorful blanket. So this was a strategic battle, but a low intelligence strategic battle at 40% or R. Blue was extremely dominant with 80% occupancy, and red was less dominant at 60% occupancy. So it was easy to say that blue would win in this. So that's why this was being done. But let me show you how things get more interesting. And let me also illustrate to you how things can get really random. So just because you have a certain set of numbers doesn't mean that an outcome is guaranteed. Okay. So for example, here, it's an aggressive model. Aggressive model means that the attacker is going towards the enemy troops. So aggressive model, this has gone through 262 time steps. Red has won. The defender has won. Defender has won because in this lattice, 50 by 50 lattice, R is 40%, which is actually rather bad. That means that the attackers don't have very good information about where the soldiers are. It's pretty fuzzy. Number of reds is 60%. Reds are everywhere on the map. This goes back to Tony's question as to how are they distributed. Here, the distribution is pretty clear. This is their territory. They're everywhere, right? It's like fighting an urban war, The city is filled with people who would defend it. They may not be most sophisticated, but they are there, and you have to get rid of them to be able to dominate. Blue, attacker, is very tiny. So you have low intelligence, your numbers are not very large. What do you expect will happen? Well, guess what? Blue becomes zero, where red has 55,000 plus left of 500,000. This is a classic case of a badly planned battle where you have less number of people, you have low levels of reliable intelligence, you are in completely dangerous enemy dominated home territory for the enemy, and it is clear that you should not have an easy time winning. But look what happens here, by golly, in that very same problem, 294 iterations, but now the blue won, for heaven's sake. All the numbers are just the same. You see, that was a very marginal loss at some level, because 50,000 on one side left out of 500,000 is actually a relatively small number. But here, the Reds are completely eliminated in their home territory with the same level of intelligence. So these two runs on exact same data, but different, obviously different random numbers, slightly different details, can lead to different results because they're sitting pretty much at the boundary of winnability or not. In one case, they got lucky because the random numbers helped them. And in the other case, they got unlucky because the random numbers did not help them. And the outcome was different. Yes, Tony.
I just don't understand these colored plots. Like that looks like a very red plot to me. What exactly is that showing?
Yeah, colored plots are not the very best ways to understand it. Basically, it is the density of reds or the number of reds. So, for example, reds are the opposite side, right?
Mhm.
So reds are the opposite side, and the blues are the attacker side. Your attacker numbers are low, so you don't expect too much attackers anyway. Uh, you, and but on the other hand, they are well spread out. In this case, perhaps the way they are spread out just works out that the numbers are enough to dominate the red. So essentially, by the time the battle ends, it doesn't matter how much reds they have; they just have no more reserves.
Okay. Okay.
If you don't have any more reserves, then you'll be killed off because these guys are still there, right? So that's the logic. So here you see, if you look at this picture on the other hand, there are many more blues.
But they're already all deployed.
They're all deployed
Gotcha.
and they have been cooked, and there are 55,000 reds left. So these blues can be taken out in number now.
Yeah. Okay.
Okay, so these two are okay. This is very interesting that we did. I haven't completely. Okay, this is fine. Epsilon A is the percentage of aggressors that are deployed. This is the R. R is the intelligence. So you expect high R to be poor intelligence, right? Low R to be higher intelligence because you have high resolution data. In fact, that's why it's called R. Picture is resolution and range. The other is epsilon A, which is the percentage of attackers, and the percentage of defenders on the lattice is given here in black. Epsilon D is 50%, epsilon D 50% in these two, and epsilon D is 75% in these two. Now let me tell you what this small a and this small d means here and here. Small a means an aggressive strategy. You go towards the attacker, and small d means a defensive strategy, which means you run away from where the attackers are. Something is very, very obvious if you look at these data. First of all, having 75% of defenders in the battlefield is not a good idea because it is much more blue here aggressive or defensive than on these two. And much more blue here means that the blue is winning. That means the attackers are winning. And the attackers are winning very, very nicely when R is small. But even when R is large and intelligence is not so much, even then the attackers are winning quite comfortably. And the reason is because the defense forces on the ground are too large. They're too vulnerable, in other words. This goes back to why did Bush deploy 40,000 troops? That was my worry. Are they too vulnerable? Well, too vulnerable if the intelligence is low, but not too vulnerable otherwise. So in this case, for defenders, because they are not using intelligence, the issue of intelligence doesn't arise. And therefore, you can see that they lose quite easily. On the other hand, here the situation is quite different. This is aggressive. Aggressive here, and this is defensive here. You can see this is more blue than that. So more of the attackers are winning in figure E than in figure C. And clearly, the winning goes down as intelligence falls. So as intelligence falls, winning goes down. As intelligence increases, winning goes up. Deployment of defenders is not very much. It's 50%, which is quite conservative. Here, the attackers are being defensive. And here, the attackers are being aggressive. So it also tells you that being defensive is a good strategy. Now, this was completely counterintuitive for me anyway, because I thought that being defensive, I was doing this part of the study more for fun. So I saw that I had like 4 absolutely superb undergrads in this problem, and we had a huge NSF grant on this at the time. So I distributed the work as a game among these 4 superb students. Any 4 of them could have joined me as postdocs. I wouldn't have known the difference. They were just that good. And this is not uncharacteristic of UB undergrads. UB undergrads, the good ones they can beat anybody anywhere in the world. So just for fun, I had them try the defensive strategy. But the idea was, you see the enemy, instead of going towards the enemy, why don't we run away from the enemy? What's so bad about that? Well, when you run away from the enemy, it turns out you win. And that was a shocker, because the expectation was just the opposite. So we decided to take a look at the lattice and see how the lattice looks like. What? Yes, Tony.
Last plot, though, it does look like there's more blue, so the attackers are more often winning. But isn't there more red, so you're also losing more battles?
Yeah, but the attackers have a lot of 429,525 left, right?
Okay.
They essentially have the whole army left,
Yeah.
and
Okay.
the other guys have used up everybody. Now, this particular picture was very revealing, because what this picture says is, by running away from the enemy, they have essentially by default defined their own fortresses, or their own sort of integrated units in the battlefield, which would be equivalent of fortresses in ancient times. You see, in ancient times, as you travel all across Europe, as you drive across Europe, if you've ever done that, even drive across the UK, you travel across India. I haven't traveled across the Middle East, especially, I mean, the Persian area. What strikes you are the distribution of fortresses. Every reasonably well-behaved hill has a fortress sitting. Cannot miss them. Some small, some huge, right? They are tourist attractions. So we are thinking of them from the standpoint of tourists. But if you are thinking of it from the standpoint of this plot, the reason is obvious, because each of those fortresses are command and control centers for the soldiers also. And that's exactly what happens here by running away. Running away by default becomes a way to construct these command control centers in the space. And because you have a cluster of people, they are essentially very, very good at defending themselves. They don't need anybody. Whoever comes near them, they can neutralize. And that was what was promoting this bizarre behavior where the defensive strategy gave us so much blue. And you're talking about the simplest possible algebra, Monte Carlo, on a tiny lattice that you can probably run on your phone nowadays, giving you highly non-trivial results that allows you to explain thousands and thousands of years worth of battles. Literally. I mean, if this is not mind-blowing statistical mechanics, I don't know what is. So, yeah, Tony.
So many questions. I'm very interested. So I see that now you've clustered them and they have essentially these strongholds, and those are very good defensive positions. And I see that they still have 400,000 troops that they can deploy, but they look completely surrounded. So how would you ever actually deploy these troops to these locations?
Yeah, that is a question that we obviously didn't address.
Okay.
So, in principle, actually, in principle, the way it works is that troop deployments tend to be very covert operations in, in, in battles like this. So you probably airdrop them in the middle of the night. You make sure that you are not visible to the local radars. You make sure that you are not making a racket, so nobody really knows much. You make sure that you are sort of in the middle of nowhere, and you have coverage. Now, this can get quite difficult in real battles, right? So, for example, a lot of people, a lot of soldiers got very injured in battles such as the Vietnam War, in battles such as the Afghanistan War, in Iraq itself, where they had trouble uh, avoiding the enemy force distribution. And many people, died because of that. They went into territories that they thought were safe, but actually were not. So there is a certain level of risk in the detail of this kind of distribution being attained. But I would venture to guess that more often than not, this is the distribution that the armies adopt because they have command control centers everywhere and in the battlefield.
I'm just thinking that this is obviously very random. It's a Monte Carlo, so they're congregate the blue troops are congregating left, right, up, down randomly. Could you impose like a directional like preference that maybe they all cluster left first, like maybe that's where our front line is or something like that?
Yeah, I think so because that way, the only way to do that would be you have to introduce some kind of strategic uh, tweaking
Mhm.
that
Yeah.
takes into
Okay.
account that intelligence, and it's doable.
Okay.
So once we got really inspired by this, I won't talk about this study actually, but uh, we wrote about 3 or 4 papers on this problem. We all have this. It's our brain, right? Uh, so one of my colleagues from pharmacy school, uh, he was talking about multiple sclerosis, which is a fairly common, I wouldn't use the word common, but fairly prevalent disease in the US. Uh, from what I have heard, I don't know if this is really true, but most Indians are not very prone to multiple sclerosis, actually. But for the Europeans or people of European descent, it's a bit more prevalent to have multiple sclerosis. Now, multiple sclerosis, what happens is that your nervous system gradually declines. So you have less control over your hands and feet. You become accident prone, eventually becoming quite immobile. But people don't die very quickly. Um, There was this famous actress, for example, who was in the Disney movies, old Disney movies. I forget her name. Um, Very pretty um, girl at the time when she originally did the movies. Um, anyway, it'll come back to me. Um, I think she had a lamb also as her friend that was in the Disney movies, of course. But anyway, the that she had multiple sclerosis very early in her life, possibly in her 30s, and she lived till her mid to late 70s. She was about maybe 15 years older than me, so had she been alive, she would be close to 80. But she died in her mid 70s, early 70s timeframe. But by the time she died, she had become really, really unwell because she was completely unable to control her body significantly. So what happens is that you have this lesion, so that they're probably some kind of strokes or equivalent to strokes, I don't really know, that happens in the brain, which damages parts of the brain. And as the number of lesions and also where the lesions are in the 7 or 8 different segments of the brain, as they grow in number, one's abilities decline. So there's a great deal of research that has long been going on in the US. And this guy, he was active in the field and he was telling me about it. And he was saying that, is it possible somehow to explore if these areas can be isolated, these damaged areas can be isolated? And I said, well, um, you know, if you put me if suppose something, I mean, for me, it's the typical example of what happens when you have a fruit that is beginning to go bad. Right? Suppose you have a banana and the banana is getting old, right? So then what do? You pick out the part of the banana that's not okay and you kind of scoop it off and throw it away. Uh, then it's as good as new, accepting that part. And since the brain is an organ that at least partially can readjust itself. Uh, so one guess I had was whether they could isolate this area of the brain that where the lesion is developed and begin some kind of and develop a protective shield around it by cutting off the linkages with that part of the brain. So it's almost like excising it. It may be sitting there, but it becomes completely inactive. That was the idea. So I called it strategic self-destruction. And so we wrote some papers on strategic self-destruction, but it was another side of the battle problem because here you don't kill anybody, but you essentially make this fortress. You isolate yourself completely by strategically cutting off all the uh, pathways that can be eliminated uh, realistically using some simple rules. The hardest part of this problem was developing those simple rules. So we wrote a paper in Europhysics Letters on this uh, 2007 or 9, I don't remember. It is a strategic self-destruction paper, and they are followed by some more medically oriented papers uh, that were also written. I was a part of that, and then it took a very interesting turn. This was around the time when there was avian influenza, avian flu among poultry. Right, there's an massive avian flu outbreak in South Korea uh, among poultry. Now that's a big problem because everybody likes to eat chicken, right? So if your chicken are all dead, then what people are very unhappy. But that's basically what happened, that pretty much the entire chicken population of South Korea had to be killed off. So naturally, it was an enormous economic loss. So one of the students who was working on this problem, a very talented student, Taeyong Kim, who is now, there is a center that does, this kind of epidemiology research, maybe, I don't remember. at University of Pennsylvania. So he's the director of that center now. So this student was our PhD student in the group at the time. He was a computer science PhD student, but he was working with a pharmacist and me and his computer science advisor. I was really not part of his committee, but I was the one who came up with the idea. So anyway, so we kind of clustered up, and Taeyong had a relative in the Department of Agriculture in the South Korean government. So he was able to get some very high quality data on how this avian flu had spread in South Korea. And the reason why the South Korean government was also interested in our study at the time was because they wanted to figure out how to best manage it. So this was what happened. Physics problem, right? Where physics shouldn't be there. The poultry that is, found all across South Korea are obviously farmed in the rural areas of South Korea. And then they're trucked into the markets. Makes sense. These farmers, they had what was effectively a sort of barter system by which they manage their farms. So they may be exchanging some money and some animals for some other animals. For example, I sell you 10,000 chickens and you sell me equivalently maybe 15 cows or something. So this kind of barter systems essentially were operational. And it was very easy for us to see, looking at the pattern of this farmer flea markets, if you will, that were happening around South Korea, that the reason why the avian influenza was spreading the way it was is because of these farmer, whatever they call them, farmer markets, if you will. And so we decided that we could study this phenomena of farmer markets and whether we could predict the spread. I haven't put it in this slide thing, but the answer is yes. So we were able to map out the spread of avian influenza among chicken in South Korea, following this and following relatively simple rules of spreading from there. So again, the same idea of, there it was attack defense, here it is coming close together and some kind of exchange of disease or containment of disease and so on. So we basically told them, to the extent I can recall, that the problem is coming from there, so please keep them low. And I think they took some steps at the time. This was 2004-5 timeframe, where they put a moratorium on having these, these markets control the sale of chicken and so on, and slowly it went down. And then they got their population built back up. So, I mean, these kind of problems are very, very good. I mean, here we did some more work on various, very different force levels. Just to show that asymmetric battles can be done. But, let me finish up because it's already past 3. So we showed that risk exposure and local intelligence play very, very important roles. Battles can really last very long if the reserve sizes are large. And this is something that is really important. You can't be going into a battle without having a very, very clear plan of what you want to accomplish and when do you want to get out. Because longer you fight a battle, the worse your chances are of winning. It's absolutely obvious from the most trivial model you can build that you do not want a long battle. It should be goal-oriented, get done, close the book, move on. Combination of aggressive and defensive strategies are the best. That I didn't describe to you guys. But if you now suppose that human beings can decide when it is a good idea to do aggression and when it is a good idea to do defense and retreat. In fact, in realistic battles, it is the command and control that decides what should be attacked and from where we should not attack and run away, move out of that area. We'll attack later. That's why we have generals and, lieutenant colonels and so on and so forth. So battles, therefore, are not just aggressive and defensive. Real battles are optimized battles. So we built a genetic model for it. That was published 2017, I think. And the idea of the genetic model was that we figure out what combination of strategies can make a war winnable within a finite time. And what we learned was any war with the right parameters, no matter how difficult, with the right combination of strategies from the genetic algorithm is winnable. Any war can be won, provided you have the right level of forces, you have the right strategy, and the right intelligence. So there is absolutely zero reason to lose a war unless you are doing something completely problematic. This widely separated force level problem has a lot to do with modeling diseases, actually. That's one reason why we did these two, because we're looking at what happens when you have widely separated force levels. And that was more in the context of disease spreading rather than battle spreading. So let me close here today. Next week, we'll move on to a different game. We'll be back to doing some more theory-ish work. One thing I want to give you a little bit of a feel upon, I don't want to overdo it because it can easily drag on, is all the stuff that we have built up on the random walk problem, that can also be applied to the problem of diffusion. And problem of diffusion is a very interesting problem. There is, of course, a diffusion equation, and one can solve a diffusion equation. But diffusion equation is a difficult equation in general to solve, non-trivial cases. But suppose you have an oil spill, suppose you have a forest fire that can spread, suppose you have a disease among animals that can spread. For all these cases, you essentially have at hand what are diffusion problems. It can even be a diffusion problem, for example, to launch a product in the market. That can also be a diffusion problem. What will help you to launch this product in such a way that people not only get the product, people also like the product and people buy the product, and therefore the diffusion pattern can be made stable and so on and so forth. So diffusion problems therefore have very broad interest. And I just want to illustrate the physics behind it a little bit. It's an endless problem. I mean, I can literally lecture to you for 5-6 lectures on diffusion problem going all over the world, but it's not worth it. This problem was very different because you couldn't have picked it up anywhere else. Diffusion you can learn yourself. So I just want to introduce the diffusion problem a little bit. And after that, take you back to nonlinear dynamics, which I introduced briefly with the Fermi-Pascual problem. I want to go back to that problem briefly and then hover around it, because by hovering around it, I can show you physics of some super important scenarios like the Kolmogorov-Arnold-Moser theorem, the Toda problem, the Sine-Gordon problem, the nonlinear Schrodinger equation problem, the connection between classical views of nonlinearity and quantum views of nonlinearity. All of these things also form a very important area that comes within modern dynamics. And I'll take you a little bit into that before we finish in early May. So that's the plan. But next week we'll start on that chapter. And I will also now ask you to think about, I think Vivek already has a project. So Tony, you can think of a project that you might want to take on and work on for this class. You know, whatever, by now you have a pretty good idea of the things we have done. So already, so you can define a problem, you can, code it up or do some combination of code and theory, whatever you feel comfortable doing, something that interests you. And then, I mean, if you ask me, I'll probably give you 30 ideas, but that's I'd rather that. Actually, it's a very good exercise. So there was a time I haven't done it lately, but in several times when I taught StatMech, instead of me giving them homeworks, I gave them some homeworks, but then I asked them to make their own problems, and I would take a look at them. That became the most, probably the most difficult challenge they ever had to take on, because making problems is not easy. So just the fact that I'm asking you guys to make your own problems, because it is very difficult to make a problem and solve it. It is very easy to make a problem and not be able to solve it. Okay, so so you have to kind of think now as both a creative person and also as a minimalist who can actually do problem reduction, because one of the biggest things we do as scientists are how to reduce problems, right? I mean, if you cannot reduce a problem, forget about it. You can't do a darn thing. So spend a week, this Thursday to next Thursday, or if you are done before that, it's even better, and send me a problem proposal where you have, let's say, kind of laid out the problem and how to calculate it. I don't want too much detail, but enough that I can see you get rolling next weekend, for example. Okay? All right. See you guys.
Yep.
Bye. Bye. And